There is a question physics has been circling for over 100 years. Not the question of how stars ignite, or what lies inside a black hole, or how galaxies arrange themselves into the vast cosmic web. Those are interesting problems, but there are still problems about things that exist. The question underneath all of them, the one that quietly waits at the bottom of every other inquiry, is harder to even say aloud without feeling slightly unsettled. Why is there a reality at all? Not how did it begin, not what is it made of, but why is anything here rather than nothing? Why do the rules exist? Why do the fields exist? Why does the stage exist on which any of this can play out? For most of recorded history, that question was handed off to philosophers and theologians. Physics did not touch it. Physics measured, calculated, predicted, and built equations that worked. It left a deeper question alone, the way you leave a closed door alone when you suspect you will not enjoy what is on the other side. That has changed. Quietly, over the past 2 decades, and with increasing momentum in the last 10 years, physics has produced a series of results that do not merely approach the question of why reality exists. They begin to answer parts of it. And the answers are not the kind that put a person at ease. They do not suggest that the universe is solid, permanent, or guaranteed. They suggest the opposite. They suggest that reality is contingent, that it did not have to exist, that it does not have to continue, and that what feels like the unshakable ground beneath every measurement, every atom, every observation, is not a foundation at all. It is a temporary condition. This is not a philosophical claim. These are measurements taken in laboratories, equations checked against data, results published in peer-reviewed journals, and numbers produced by the largest scientific instruments humanity has ever built. The unsettling part is not what physics has discovered about the beginning of reality. The unsettling part is what those discoveries imply about right now, about this very moment, about whether the structure of everything you can see, touch, and measure is as stable as it appears. It is not. And to understand why, the first place to look is the most recent number physics has produced about the field that fills all of space. Before we dive deeper, if this kind of content genuinely interests you, consider subscribing, because what you're about to see only gets more surprising from here. And I post videos like this every single day. Now, let's continue. In July of 2012, physicists at the European Organization for Nuclear Research, working with a Large Hadron Collider, announced the discovery of the Higgs boson, the particle responsible for giving other particles their mass. The missing piece of the standard model of particle physics. It was a genuine triumph. Decades of theoretical work, billions of dollars of engineering, and the largest scientific instrument ever constructed, all converged on a single measurement. And the measurement arrived. The mass of the Higgs boson was determined to be approximately 125.09 giga-electron volts. You might reasonably assume this is just a number, a data point to be filed and then surpassed by the next discovery. But between 2012 and 2022, 4 independent research groups ran that number through the equations governing the electroweak field, the fundamental field that the Higgs boson maintains across all of space. What they found is that at 125 giga-electron volts, our vacuum sits in a state physicists describe with a single technical word: metastable. Metastable does not mean stable. It means stable for now, under current conditions, unless something disturbs it. Imagine a glass balanced on the very edge of a table. It has been sitting there for 13.8 billion years. Nothing has knocked it off. You might look at that glass and conclude that it is fine, that it will remain fine forever. But the physics of the situation does not tell you the glass is safe. It tells you the glass has not fallen yet. Those are not the same statement. Our vacuum, the invisible substrate of space itself, the field that sets the rules for every particle and every force in the universe, is that glass. The electroweak calculations indicate that it is not sitting in its lowest possible energy state. It is sitting in a local minimum, a shallow dip that feels like the bottom but is not the bottom. There is a lower state available, a true vacuum, and the difference between where we currently are and where the equations say we could fall is the difference between the universe as it exists and a universe in which nothing we recognize can exist at all. Reality is not resting. It is holding its position. To understand what metastable actually means at the physical level, you have to look one layer deeper into what the vacuum actually is. The vacuum of space does not feel like anything. You cannot touch it, taste it, or measure it directly with your hands. It registers as absence, as nothing. But in quantum field theory, the vacuum is not nothing. It is a state, a specific energetic condition that permeates all of space at all times. It is the floor of reality, the baseline from which every particle, every force, every physical interaction is measured, and the floor, according to the calculations, is not the real floor. In 1980, physicists Sidney Coleman and Frank De Lucia worked out the mathematics of what happens when a vacuum is metastable. Their equations described a process called bubble nucleation. At any point in space, at any moment in time, quantum fluctuations can push a small region of the false vacuum over the energy barrier and into the true vacuum state. This creates a bubble, a sphere of true vacuum expanding outward in all directions at the speed of light. Think of a container of supercooled water, water that has been chilled below freezing but has not yet turned to ice because there is no nucleation site for crystals to form around. The water is metastable. It looks like water. It behaves like water. But introduce a single dust particle, a vibration, any small disturbance, and the entire container freezes in an instant. The phase transition is immediate and total. The bubble of true vacuum works the same way, except the container is the universe, and the phase transition does not produce ice. It produces a region of space where the physical constants are different, where the mass of the electron, the strength of electromagnetism, the rules governing atomic structure are all reset to different values. Values under which atoms as we know them cannot exist, under which chemistry cannot occur, under which nothing currently in this universe can persist. The bubble expands at the speed of light. This is the detail that removes any possibility of response. Light is the fastest signal the universe permits. Information cannot travel faster than light. That means the image of the bubble's expanding wall, the photons bouncing off the boundary between false and true vacuum, travels at exactly the same speed as the boundary itself. You would not see it coming. There is no version of events in which you see it coming. The wall and the news of the wall arrive at the same instant. The last thing the universe would permit you to know is that this was happening. At the moment of arrival, it has already happened. Physics does not offer a detection mechanism. It offers only a description of disappearance. This brings us to the number that quietly started a wave of unease in theoretical physics. A number that suggests the instability is not a small technical issue, but something far more fundamental about the foundation of K-law physical law. There is a number in physics that no one can explain. Not slightly off, not requiring a small correction, but wrong by a factor that has no precedent in the history of science. a factor so absurdly large that it suggests something fundamental about our understanding of reality is missing. The number is 10 to the power of 120. Here is the problem. Quantum field theory, the most precisely tested scientific framework ever constructed, accurate to more decimal places than any other theory in any discipline, predicts a specific value for the energy density of empty space. The energy that the vacuum itself carries, even when stripped of all matter and radiation, the prediction is a very large number. Then physicists measure the actual energy density of the vacuum by examining the expansion rate of the universe, the behavior of distant galaxies, and the geometry of space-time on the largest accessible scales. They got a number. The measured number is smaller than the predicted number by a factor of 10 to the 120th power. To understand what that gap means, consider this. There are roughly 10 to the 80th atoms in the entire observable universe. 10 to the 120th is not just larger than that. It is larger by 40 orders of magnitude. If you took the number of atoms in the observable universe and raised it to the power of 1.5, you would only begin to approach the size of this discrepancy. This is not a rounding error. It is the largest disagreement between a theoretical prediction and an experimental measurement in the history of physics. And it has been sitting in the equations, unresolved, for more than 60 years. Imagine you are an engineer, and you calculate that a bridge should weigh 120 tons. You then go and weigh the bridge. It weighs 1 gram, and the bridge is still standing. That is the vacuum energy problem. The calculation and the measurement are so far apart that the fact that anything coherent exists at all requires an explanation physics does not currently possess. The standard model predicts a vacuum that should have torn reality apart before the first star ever formed. Something is wrong at the level of the foundations. No serious physicist will tell you otherwise, however carefully they word it in public. And here is the question that follows. If the calculation is off by that much and reality is still here, what is actually holding it up? One possibility is that the vacuum energy problem is not a flaw at all. Perhaps the numbers were always going to be exactly what they are. Perhaps the constants that govern our reality were not accidents. That is where the next layer begins, and it is where the question of fine-tuning enters. Before reaching it, though, it is worth being precise about what the bubble nucleation scenario actually says. Not what it suggests as a distant theoretical possibility, but what the equations of quantum field theory state as a direct consequence of a metastable vacuum. The bubble of true vacuum, once formed, expands at the speed of light in all directions simultaneously. It is not a shock wave. It is not radiation. It is a boundary, a surface, where the rules of physics on one side are different from the rules on the other, and where the values of the fundamental constants change discontinuously. Step across that boundary, and you are in a region where the electron has a different mass, where electromagnetism operates with different parameters, where the nuclear forces holding atoms together have different strengths. Everything built from the physics of the false vacuum, every atom, every molecule, every structure, ceases to be possible. Now consider the geometry of the situation. The bubble wall moves at the speed of light. Light from the bubble wall also moves at the speed of light. The signal carrying information about the approaching wall and the wall itself travel toward you at the same velocity. They arrive together. There is no gap between the warning and the event. Imagine standing in a field at night. Something is moving toward you in complete darkness. You cannot see it. You cannot hear it. The only way you would know it was there is if it emitted a flash of light at the very instant it reached you. That flash would be the first and last thing you ever perceived. The event and its announcement would be simultaneous. There is no before. This is not a limitation of current technology. It is not a problem better telescopes or faster computers will eventually solve. It is a geometric consequence of the speed of light being both the speed of the threat and the speed of the information about the threat. No instrument, no matter how sensitive, can receive information faster than the information itself can travel, and the information travels at the same speed as the wall. Physicists have searched for ways around this constraint. There are none. If a bubble forms close enough to reach us before cosmic expansion carries it away, we will not detect it in advance. The last measurement our instruments make will be normal. The physics of our vacuum will appear stable and intact, right up to the moment that it is not. The silence of our detectors is not evidence of safety. From this side of the wall, safety and destruction look identical. Now, perhaps the instability is not a flaw in the construction of reality. Perhaps the numbers were always going to be exactly what they are. That is where the next layer begins, and it turns out to be more disturbing than the one we just left. There are numbers written into the structure of reality, not numbers that scientists invented to describe what they observed, but numbers that had to be exactly what they are for observation to be possible at all. Change them, and the universe does not become a different universe. It becomes nothing. Not a different kind of something, but nothing capable of structure, complexity, or time. The gravitational constant is one of these numbers. Gravity is the weakest of the four fundamental forces, weaker than electromagnetism by a factor of 10 to the 36th power, weaker than the strong nuclear force by a factor of 10 to the 38th. It barely registers at the subatomic scale. You need masses the size of planets before it becomes the dominant force in the room. And yet it is the force that shapes the universe on the largest scales, that pulls matter into stars, that collapses stars into the furnaces that forge heavy elements, that organizes those elements into galaxies, and the galaxies into the large-scale structure of everything we can observe. Now consider what happens if you adjust the gravitational constant upward by 1 part in 10 to the 40th power, 1 part in 10,000, billion, 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 billion. A change so small it has no analogy in ordinary experience. No object you could construct could demonstrate the difference. The universe collapses. Not slowly, not after a long period of normal evolution, but in the first seconds after the Big Bang. Matter pulls together too quickly. There is no time for stars to form, no time for nuclear fusion to begin, no time for the carbon, oxygen, and nitrogen required for chemistry to be synthesized. The entire mass of the observable universe implodes before the first atomic nucleus stabilizes. Now adjust the gravitational constant downward by the same amount. The opposite failure occurs. Matter disperses too quickly. Gravity cannot gather hydrogen into stars. The universe becomes a thin, cold, expanding fog. No fusion, no elements heavier than hydrogen, no planets, no chemistry, no time for anything to happen. The gravitational constant sits between these two failures with a precision that has no explanation within the standard framework of physics. And gravity is only one dial. There are others, each set with the same inexplicable precision, each pointing at the same question that the gravitational constant raises and does not answer. In 1953, the British astrophysicist Fred Hoyle did something that has no real parallel in the history of science. He predicted the existence of a specific physical property of the carbon nucleus, not from an experiment, not from a measurement, not from a mathematical framework that required it. He predicted it from the fact that he was alive. The reasoning ran like this. Hoyle was studying stellar nucleosynthesis, the process by which stars forge elements heavier than hydrogen and helium. He knew that carbon is the backbone of all known chemistry. Every living cell, every protein, every strand of genetic material is built on carbon's ability to form stable bonds with other atoms. Without carbon, the kind of chemistry that produces self-replicating structures does not occur. He also knew how stars make carbon. Inside a star, 3 helium nuclei must collide and fuse to produce a single carbon nucleus. This process, called the triple alpha reaction, requires something specific. The combined energy of 3 helium nuclei at stellar temperatures must closely match a resonance energy of the carbon nucleus itself, a kind of quantum tuning fork. If the energies align, the reaction proceeds efficiently. If they do not align, carbon does not form in meaningful quantities. Hoyle calculated what that resonance energy would have to be for carbon to form abundantly enough to produce a universe containing life. He got a number. Then he walked into a laboratory and told the experimentalists exactly where to look. They found it, precisely where Hoyle had predicted. Consider what that means. Hoyle did not derive the resonance from first principles. He derived it from existence. He said, in effect, we are here. Carbon chemistry is the reason, therefore the carbon nucleus must have this property. He used the fact of his own presence in the universe as a measuring instrument, and the universe confirmed the measurement. The carbon resonance sits at approximately 7.6567 mega electron volts. The resonance of oxygen, the next element in the chain, sits just low enough that carbon is not immediately converted into oxygen during stellar fusion. Both values are precisely positioned. If the carbon resonance were 4% lower, carbon would not form in significant quantities. If the oxygen resonance were 0.5% higher, all the carbon would convert to oxygen before it could be ejected into space. Both dials are set. Both are tuned to values that permit the specific chemistry required for the existence of any observer asking why they are set that way. This cannot be dismissed as coincidence. It is a second example of a physical constant sitting at a value that has no derivation from deeper physics and no explanation within the standard model. It simply is what it has to be for the question to be asked at all. Then there is the cosmological constant. Einstein called it his greatest mistake. He introduced it in 1917 to make his equations of general relativity produce a static universe, because the idea of an expanding cosmos seemed physically unreasonable at the time. When Edwin Hubble demonstrated in 1929 that the universe was, in fact, expanding, Einstein removed the term and reportedly wished he had never added it. Then, in 1998, it came back. 2 independent teams of astronomers studying the brightness of distant supernovae to measure the expansion rate of the universe found something their instruments should not have been capable of detecting. The expansion of the universe is not slowing down, it is accelerating. Something is pushing space apart faster and faster against the gravitational pull of all the matter in the observable universe. That something required a term in Einstein's equations, the cosmological constant, the energy of empty space, the same quantity Einstein had added and then removed. Its observed value is approximately 1.1 times 10 to the negative 123rd power in units of inverse meters squared. Now recall the vacuum energy problem from earlier. Quantum field theory predicts a value for that same quantity that is 10 to the 120th power larger than what we measure. Set that discrepancy aside for a moment and look at the cosmological constant from a different direction. Ask what happens if you change it. If the cosmological constant were slightly larger, not by the absurd factor the quantum calculation is off by, but by just a few times its observed value, the repulsive effect of vacuum energy would have overwhelmed gravity in the early universe before matter could cluster into galaxies. Space would have expanded too quickly. Matter would have dispersed into a cold, thin, structureless gas. No stars, no planets, no chemistry, no time for anything interesting to occur. If the cosmological constant were negative, if vacuum energy pulled instead of pushed, the universe would have collapsed back on itself within the first billion years. A big crunch before the first generation of stars completed their lives. Imagine a tightrope stretched across a canyon. The tightrope is one value wide. Everything to the left is one kind of catastrophe. Everything to the right is another. The cosmological constant is walking that tightrope. It has been walking it for 13.8 billion years. Physics does not explain how it found the rope. Physics does not explain why the rope is positioned exactly where it is. The cosmological constant, the gravitational constant, the carbon resonance. 3 numbers, 3 dials set to values that permit structure. 3 settings that are not derived from anything deeper in the current framework of physics. You might reasonably ask whether this is simply a failure of present-day physics, whether some future theory will eventually derive these values from first principles and the mystery will dissolve. To understand why most physicists no longer expect that answer, the next step is to look at the landscape that string theory produced when researchers actually tried to find that deeper theory. For decades, physicists operated on an assumption so basic that it was rarely stated out loud. The assumption ran like this: the constants of nature have the values they have because a deeper theory will eventually derive them. The gravitational constant, the cosmological constant, the mass of the electron, all of these numbers feel arbitrary because we do not yet have the framework that makes them necessary. Once we find that framework, the numbers will fall out of the equations the way the orbits of planets fall out of Newtonian gravity. They will stop being mysteries and become inevitabilities. String theory was supposed to be that framework. It replaced point particles with one-dimensional vibrating strings. It required extra dimensions of space beyond the 3 we experience. For roughly 20 years, theoretical physicists invested enormous effort in developing it because it appeared to be the kind of deep structure that would finally explain why the constants are what they are. Then, in 2003, Leonard Susskind worked out the calculation that changed everything. He determined how many distinct vacuum states string theory actually predicts. Each vacuum state corresponds to a different way the extra dimensions of the theory can be curled up and configured. Each configuration produces a different set of physical constants, a different gravitational constant, a different cosmological constant, a different mass for the electron, a different universe with different rules, different chemistry, different everything. The number of distinct vacuum states is approximately 10 to the power of 500. It is worth pausing on what that number means. 10 to the 500 is not a large number in the way a billion is a large number. It is a number of a categorically different kind. The total number of atoms in the observable universe is 10 to the 80th. 10 to the 500th is larger than that by 420 orders of magnitude. It is a number so vast that if you spend the entire age of the universe counting, you would not reach a fraction of a fraction of a fraction of it. String theory does not predict that our vacuum exists. String theory predicts that our vacuum is one entry in a catalog so large that the word catalog loses its meaning. The theory does not tell you why the cosmological constant has the value it has. It tells you that somewhere in the landscape of 10 to the 500 possibilities, there is a vacuum with that value, alongside vacuums where the cosmological constant is 1,000 times larger, 1,000,000 times smaller, and every other value in between. This is not an explanation. It is the formal abandonment of the expectation of an explanation. A theory that predicts every possible universe predicts nothing about any specific universe. You have not explained the number. You have dissolved the question by making every answer equally valid. But what if there is no choice involved at all? What if the landscape is not a theoretical embarrassment, but a physical reality? What if all 10 to the 500 vacuums actually exist? In 1986, the Russian-American cosmologist Andrei Linde published a paper that took the standard model of cosmic inflation and followed it to its logical conclusion. The conclusion was not comfortable. Inflation is a theory that in the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion. Space expanded faster than light, doubling in size every tiny fraction of a second, stretching a region smaller than a proton into something larger than a galaxy in an interval too brief to measure by any ordinary standard. This expansion smoothed out the early universe, explaining why the cosmic microwave background radiation is so uniform and why the large-scale structure of the universe looks the way it does. In the standard version, inflation eventually ends. The exponential expansion slows. The energy driving it converts into matter and radiation, and the universe settles into the more gradual expansion we observe today. Linde showed that in most realistic versions of inflation, it does not end everywhere at once. It ends locally. In what is called eternal inflation, the exponential expansion is driven by a quantum field. Quantum fields fluctuate. In some regions of space, the fluctuations cause the field to drop into a lower energy state, ending inflation locally and producing what looks from the inside like a Big Bang. A new region of space filled with matter and radiation, cooling and expanding, potentially forming galaxies and stars and chemistry. In other regions, fluctuations push the field higher, keeping inflation going. Inflation does not stop. It keeps producing new regions, new pockets, each one a separate universe with its own physical constants drawn from the landscape of possibilities that string theory describes. Imagine an infinite foam of soap bubbles, each one forming inside an expanding medium that never stops producing new bubbles. Each bubble is a universe. Each universe has its own rules. Most bubbles are empty. Most collapse before anything interesting forms. A small fraction have constants in the right range for stars to ignite. A smaller fraction still permit chemistry. A smaller fraction still permit biology. We live in one of the rare bubbles where the question can even be asked. The implication is that the fine-tuning problem dissolves. Not because someone set the dials, but because every dial setting exists somewhere. You observe a universe with life-permitting constants, not because those constants were chosen, but because only in universes with life-permitting constants can observers exist to notice them. This sounds like a solution. It is not. A theory that explains everything by positing that everything exists is a theory that explains nothing in particular. You cannot test it. You cannot falsify it. Even if every possible universe exists, you still have to explain why the laws that permit inflation exist, why quantum fields exist, why the mathematics of string theory applies to anything at all, rather than nothing applying to nothing. The mystery is not closed. It has been moved one level deeper. and the level below is darker than the one we just left. There is, however, an answer to the fine-tuning problem that is logically airtight. It requires no multiverse. It requires no deeper theory. It requires no mechanism at all. It simply points at a fact so obvious that it is almost impossible to see. The way you cannot see the air in a room until something moves through it. The answer is this: you are here. In 1974, the British physicist Brandon Carter formalized what he called the anthropic principle. The core of it is a single observation. The conditions you observe in the universe are not a random sample of all possible conditions. They are a sample filtered by the requirement that you exist to observe them. You cannot observe a universe that does not permit observers. Therefore, the universe you observe will always appear to have constants compatible with your existence. Not because someone arranged them, not because they were selected from a landscape, simply because the alternative universes, if they exist, contain no one to notice that they exist. It sounds reassuring. It sounds as if the mystery dissolves. Consider a man who survives a firing squad. 20 trained marksmen standing 10 meters away, all firing simultaneously. Every bullet misses. The man walks away. He might ask, what are the odds of that? He might feel that some extraordinary explanation is required. But there is a simpler observation available. If the firing squad had succeeded, he would not be asking the question. The fact that he is standing there asking is already proof that he survived. The question selects for the answer. The anthropic principle applies the same logic to the universe. The fact that you are asking why the constants permit life is already proof that you live in a universe where the constants permit life. No further explanation is required. Here is where the logic becomes genuinely disturbing. Not because the anthropic principle is wrong. It is not wrong. It is impeccably correct. What is disturbing is what correct means in this case. Correct means that the constants of nature could be arbitrary, completely arbitrary. They do not have to have the values they have for any reason deeper than the fact that in universes where they have other values, no one asks. The universe does not have to be fine-tuned. It does not have to be designed. It only has to be the kind of universe in which the question can be formed. And that requirement, it turns out, is the only filter applied. You are not the product of a plan. You are the product of a filter. The filter is your own existence. The plan, if there ever was one, is indistinguishable from the absence of a plan when observed from the inside. This is the most unsettling answer in science. Not because it is incorrect, but because it is correct and says nothing. It tells you that reality did not have to be this way. It tells you that the apparent precision of the constants is a consequence of your position as an observer, not a feature of the universe itself. Reality is not fine-tuned for you. Reality is filtered by you. The difference is everything. If this question is sitting with you, take a moment to like the video and subscribe so you can follow where the rest of this leads. Now, we keep going. This brings us to the question of what reality is actually made of at the level below the constants, below the fields, below the particles, below the forces. What physics found when it pushed past the numbers and into the structure underneath. Every physical process you have ever observed follows a rule, not a suggestion. A rule with no known exceptions, operating at every scale from subatomic to cosmological, for as long as physics has been able to measure anything. And nobody knows why the rule is the rule. When a physical system moves from one state to another, it does not take a random path. It takes the specific path for which a mathematical quantity, called the action, is minimized. The action is computed from the energy and the geometry of the path. Among all the infinite paths a system could take, nature selects the one that makes this quantity an extremum. This should not work. There is no obvious mechanism by which a particle, before moving, evaluates all possible trajectories and selects the optimal one. The particle has no information about the paths it did not take. And yet, the path it takes is always the optimal one. Imagine every physical process as a traveler who needs to get from one city to another. The traveler does not wander. The traveler takes the road that is optimal according to a specific mathematical criterion, not a criterion the traveler chose. A criterion written into the structure of space and time itself. Every process in the universe, from the orbit of a galaxy to the decay of a single atom, obeys this criterion without exception and without awareness. Richard Feynman reformulated this in quantum mechanics and made it stranger rather than simpler. In Feynman's formulation, a quantum particle does not follow a single path. It follows all paths simultaneously. Every possible trajectory through space and time contributes to the particle's final behavior. The classical path, the one that minimizes the action, is simply the one where contributions from nearby paths add together constructively. The other paths cancel out. What this means is that the principle of least action is not a rule imposed on nature from outside. It emerges from the quantum substrate as a statistical inevitability. The universe explores all possibilities. The minimum action path survives the interference. Everything else cancels. But this shifts the mystery rather than dissolving it. Why do quantum amplitudes combine in exactly the way that produces least action behavior at larger scales? Physics states the rule with extraordinary precision. It does not state where the rule comes from. It has been sitting in the equations since the 1740s, unchanged and unexplained. The universe is not just following equations. It is following optimal equations. A universe that simply followed some equations would be unremarkable. A universe that follows the mathematically optimal path through every process at every scale is a universe that looks, from the outside, like a computation, which raises a question nobody in the field is comfortable with. If it is a computation, what is it running on? To understand how deep the structure goes, we have to look at what space itself is made of at the smallest scales physics can currently describe. The intuition about space is that it is continuous, that between any 2 points, no matter how close together, there is always another point, that you could zoom in forever, and space would still be there, smooth and uninterrupted, an infinite substrate with no smallest unit. That intuition is almost certainly wrong, and the mathematics that says so has been sitting in peer-reviewed journals since the 1980s. Loop quantum gravity was developed over more than a decade by Roger Penrose, Lee Smolin, Carlo Rovelli, and their collaborators. Its central claim is that space is quantized. It has a minimum unit of size below which the concept of distance loses its meaning entirely. That minimum unit is the Planck length, approximately 1.61 6 times 10 to the negative 35th meters. To give a sense of scale, a proton is approximately 10 to the negative 15th meters across. The Planck length is 20 orders of magnitude smaller than a proton. If an atom were scaled up to the size of the entire observable universe, the Planck length would still only be roughly the size of a tree. Imagine a photograph. Zoom in far enough, and the continuous image resolves into individual pixels. Each pixel is either on or off, a discrete unit with no structure below its own scale. The image looks smooth from a distance because the pixels are too small for your eye to resolve them individually. Space, in loop quantum gravity, has pixels The pixels are at the Planck scale. The smoothness you experience is a low-resolution illusion generated by the fact that everything you have ever interacted with is enormously larger than the pixel size. At the Planck scale, space is not a smooth fabric. It is a network. A discrete web of nodes and links called a spin network. Each node represents a quantum of volume. Each link represents a quantum of area. The geometry of space emerges from this network at larger scales, the way temperature emerges from the average motion of molecules. Temperature feels continuous. At the molecular level, it is discrete collisions. Space feels continuous. At the Planck level, it is discrete geometry. Now, what generates the spin network? What decides the geometry of the nodes and links? The spin network is not a static object. It evolves. It changes according to specific equations. But the network itself is not made of anything. It is not embedded in a background space. The spin network is space. There's nothing beneath it. If space is a network of discrete quanta, and if the network is all there is, then reality at its most fundamental, accessible level is not made of stuff. It is made of connections between abstractions. Not things in relationships, but the relationships themselves, with no underlying substance that the relationships are relationships between. But if space is discrete, what about the rules that govern it? Here is where physics, in the present day, runs into a wall it has not found a way around. Physics has two theories. Both are correct. They cannot both be correct at the same time. This is where the field has been for 100 years, and there is no sign of movement. General relativity describes gravity and the large-scale structure of the universe. Space-time curvature, black holes, the expansion of the cosmos, the bending of light around massive objects. Its predictions have been confirmed by satellite navigation systems, by gravitational wave detectors, by the photographed shadow of a black hole. It is a theory of smooth, continuous space-time geometry. Quantum field theory describes the other three fundamental forces and all known particles. Its predictions have been confirmed to more decimal places than any other theory in any scientific discipline. It is a theory of discrete, probabilistic quantum fields. When you try to combine them, when you try to write down an equation that describes gravity in quantum terms, the mathematics breaks. The equations produce infinities, not large numbers, actual infinities, values that diverge without limit and have no physical interpretation. The mathematics simply stops working. Imagine two maps. One map covers everything west of a river. It is extraordinarily detailed, accurate to the millimeter, tested against every landmark. The other map covers everything east of the river with the same precision. But neither map includes the river itself. And the river is where the most interesting things happen. Black holes are the river. The Big Bang is the river. The Planck scale is the river. Physics has two perfect maps with a gap between them, and the gap is exactly where the origin of reality is located. String theory proposes one way to bridge the gap. It requires 10 or 11 dimensions of spacetime. It predicts 10 to the 500 vacuum states. And after 50 years of development, it has produced no unique experimental prediction that distinguishes it from competing theories or from no theory at all. Loop quantum gravity produces a discrete, quantized spacetime and avoids the infinities. But it has not successfully incorporated the other three fundamental forces. It describes quantum space. It does not describe quantum matter in quantum space. As of the present moment, no theory unifies general relativity and quantum mechanics. No theory describes what happens inside a black hole, where both must apply. No theory explains the moment of the Big Bang, where both are required and both break down. This incompleteness is not accidental. It may not be a temporary gap. It may be structural. And if it is structural, the question is not when physics will fill it. The question is whether the contents of the gap are even the kind of thing physics can describe. What is the map supposed to show when the territory is the absence of all maps? In 1931, a 25-year-old Austrian mathematician named Kurt Gödel published a proof that changed the foundations of mathematics permanently. Not a conjecture, not a hypothesis, a rigorous demonstration of something the mathematical community had assumed was impossible, and that, once demonstrated, could not be refuted. The proof said this: any formal mathematical system powerful enough to describe basic arithmetic contains true statements that cannot be proven within that system. Not statements that are merely difficult to prove, but statements that are true, genuinely and verifiably true, and that the system itself is constitutionally incapable of proving. The incompleteness is built into the structure of any sufficiently powerful formal system by mathematical necessity. To see why this matters for physics, you have to understand what a physical theory is. A physical theory is a formal system. It is a set of axioms, a set of rules for deriving consequences from those axioms, and a set of predictions about what will be observed. The standard model of particle physics is a formal system. General relativity is a formal system. Any theory of everything, any complete description of reality would be a formal system. Gödel's theorem applies to formal systems. Imagine a library that contains every book ever written, including books about the library itself. The library seems complete, but Gödel showed that any sufficiently rich library of this kind must contain statements about itself that the library cannot verify. There are truths about the library that can only be seen from outside the library, from a position that, if the library is everything, does not exist. Apply this to physics. If the universe operates according to rules powerful enough to generate the complexity we observe, then, by Gödel's theorem, there are true statements about the universe that cannot be proven from within it. There are facts about reality that are real, not arbitrary, but that cannot be derived from any theory constructed inside the reality they describe. This is not a statement about the limits of human intelligence. It is a mathematical theorem about the structural relationship between a system and its own description. No amount of progress in physics can produce a complete description of reality from inside reality. Sit with that for a moment. The full theory of everything cannot be found by anyone living inside the thing it describes. Not eventually. Not with better tools. Never. The incompleteness is not a gap we have not yet reached. It is the shape of the space we are standing in. The view from inside cannot see the outside. There is no outside available. But what if the problem is not the rules? What if the problem is the number of realities those rules permit? What if every time the rules are applied and a decision is required, every possible outcome happens simultaneously, and the universe we experience is only one thread in a structure of infinite branching? In 1957, a Princeton graduate student named Hugh Everett III submitted a doctoral thesis proposing a solution to the measurement problem in quantum mechanics. The solution was mathematically clean, logically consistent, and required no additional postulates beyond the standard equations of quantum theory. His thesis committee found it deeply uncomfortable. His advisor, John Wheeler, spent months trying to persuade him to soften the implications. Everett declined. The implications, he argued, followed directly from the mathematics. If the mathematics was correct, the implications were correct. The implications were these: the universe never makes a choice. Quantum mechanics describes physical systems using a wave function that encodes all possible states the particle could be in, with different probabilities attached to each. When you measure the particle, the standard interpretation says the wave function collapses. The superposition of all possible states resolves into one definite outcome. Everett asked a simple question: what collapses the wave function? What physical process causes a superposition to resolve into a single outcome? The standard interpretation gives no mechanism. It simply states that measurement causes collapse without defining what a measurement is, without identifying the physical boundary between quantum systems and measuring devices. Everett's answer was that nothing collapses the wave function, because the wave function never collapses. What appears to be a collapse is actually a branching. When a quantum event occurs with two possible outcomes, the universe does not select one. Both outcomes happen. The universe splits into two branches, one containing each outcome. Both branches are equally real. Both contain observers who experience a definite result. From inside each branch, the measurement appears to have produced a single outcome. From outside the branching, both outcomes exist simultaneously. Imagine a river reaching a fork. The water does not choose left or right. It goes both ways. The left branch and the right branch both exist. Both carry water. Both continue downstream. An observer floating on a leaf in the left branch sees only the left branch. They conclude that the river chose left, but the river chose nothing. It simply flowed. Every quantum event is a fork. Every radioactive decay, every photon hitting a surface, every electron settling into a spin state. Right now, in this moment, there are versions of this conversation happening in branches where slightly different words were chosen. In branches where the reader stopped 3 paragraphs ago. The branching is not science fiction. It is what the mathematics of quantum mechanics predicts when you take it seriously. The disturbing part is not the existence of the branches. The disturbing part is what their existence implies about the branch you are in. You did not arrive here by selection. Every branch contains an observer who believes they are in the only branch. You are one of an uncountable number of instances of yourself, each equally convinced that their experience is the real one. The question is not whether this is true. The question is what selects the branch you experience. And the answer physics currently offers is nothing. The selection is an illusion generated by the structure of experience itself. The many worlds interpretation produces an immediate objection. If every quantum event splits the universe into branches, why do we never see the splitting? Why does the world ongoing process? Let the process pause, and the pattern simply ceases. Reality, according to the picture that emerges from quantum mechanics taken at face value, may be more like that wave than like the stone we instinctively imagine it to be. This is the conclusion that physics has been quietly approaching for a century without ever stating it cleanly. The universe did not have to exist. It does not have to be stable. It does not have to continue. The reason it currently displays the specific character it does, definite, located, structured, ordered into atoms and stars and observers, is that it contains systems that interact with it, and in interacting with it, contribute to constituting it. We are not bystanders watching reality unfold. We are part of what holds reality in its current shape. That conclusion is not comforting. It was never going to be. Before closing the loop on what physics currently does and does not understand, there is one more thread worth pulling, because it cuts directly across the assumption most people carry without noticing. The assumption that time is what is described by a single wave function, The equation they wrote down is now known as the Wheeler-DeWitt equation. It is the closest thing physics has ever produced to a wave function for everything. The equation has a peculiar feature. It contains no time variable, not a hidden time variable that can be extracted through clever mathematical manipulation, not an implicit time variable disguised in some change of coordinates. The equation simply does not contain time at all. Time, the dimension we experience as the medium through which events unfold, the parameter that appears in every other fundamental equation in physics as the independent variable against which everything else evolves, is absent from the equation that purports to describe the quantum state of the universe. One could argue that this is a technical artifact, that the equation is incomplete, that some refinement will eventually restore the missing dimension. That is a defensible position. It is also the position that physicists have held for over half a century, while the time variable has stubbornly refused to reappear. At a certain point, the absence itself becomes the data. The result follows from the structure of general relativity combined with quantum mechanics. General relativity treats time as a dimension of spacetime, not as an external clock running in the background. When you quantize gravity, time gets absorbed into the geometry of the system. It becomes a degree of freedom of the universe, rather than a backdrop against which the universe evolves. The output is an equation describing all possible states of the universe simultaneously, with no preferred sequence, no before, no after. Compare this to a photograph. A photograph does not depict motion. It captures all the information about a moment in a single static object. The Wheeler-DeWitt equation describes the universe in the way a photograph describes a face. Every configuration the universe has ever occupied or will ever occupy is encoded in the wave function at once. The sequence we experience as the flow of time is not part of the fundamental description. Einstein arrived at a related conclusion much earlier. His special theory of relativity, published in 1905, produced a consequence that he understood clearly and that most people have still not fully absorbed. There is no universal present moment. There is no single instant that is now for the entire universe simultaneously. In Newtonian physics, time was absolute. The present was the same for everyone. Two observers, no matter where they were or how fast they were moving, shared a single now. Events occurred in a definite order. Before and after were objective facts about the universe. Relativity dismantled that. Two observers moving at different velocities disagree about whether two distant events occurred at the same moment. There is no fact of the matter about which observer is correct. Simultaneity is not a property of events. It is a property of reference frames, and reference frames are relative. Hermann Minkowski, who had been Einstein's mathematics teacher, drew the conclusion explicitly in 1908. If simultaneity is relative, then the distinction between past, present, and future is also relative. The only objective structure is the four-dimensional geometry of spacetime, in which all events, past, present, and future, exist as fixed points. No point in this geometry is privileged as the present. This is the block universe interpretation. The idea that all moments of time exist with equal reality, in the same way that all points in space exist simultaneously. Your birth and your death are both already there, fixed locations in a four-dimensional structure, as real as the moment you are reading this sentence. The experience of time passing, of the present sliding from past toward future, is not a feature of the universe itself. It is a feature of consciousness moving through a static structure. Imagine a novel. Every page of the book exists at once on a shelf. The characters within the story experience events in sequence, but the sequence belongs to the reading, not to the object. The block universe suggests that what we call the flow of time is the reading, not the book. But if all moments coexist, why do we experience them in only one direction? Why do we remember the past and not the future? Why does heat flow from hot to cold and not the other way around? Why do acts break and never reassemble? Most fundamental physics is symmetric in time. Take any equation describing a basic physical process and run it backward. The reversed process is equally valid, equally permitted by the laws. A film of two billiard balls colliding looks physically plausible whether played forward or backward. At the deepest level, both directions are mathematically equivalent, and yet time has a clear direction. The asymmetry has to come from somewhere, and the source is not a law, it is a count. Entropy is a measure of disorder, of the number of distinct microscopic arrangements that produce a given macroscopic appearance. A broken egg has higher entropy than an intact one because vastly more molecular configurations correspond to broken than to intact. The second law of thermodynamics states that entropy tends to increase, not because nature has a preference for disorder as a matter of principle, but because disordered configurations vastly outnumber ordered ones. Random shuffling almost certainly leads to a high entropy outcome, not by law, by the weight of numbers. This is the arrow of time. The thing that makes the past feel fixed and the future feel open is not encoded in the fundamental equations. It emerges from the initial conditions, specifically from the fact that the early universe was in an extraordinarily low entropy state, smooth, uniform, improbably ordered. Everything since has been a long statistical drift toward equilibrium. Picture a room in which someone has spent hours arranging grains of sand into an intricate pattern. You walk in, sneeze, and the pattern is gone. The sneeze did not destroy the pattern by any law against orderly sand. The sneeze introduced random motion, and random motion overwhelmingly favors the vastly more numerous disordered arrangements. The pattern was the anomaly. The mess is the default. The universe began as the pattern. It has been becoming the mess ever since. The direction of time is not a built-in feature of physics. It is the memory of an extraordinary starting condition that physics has never been able to explain. The arrow points forward because we began in a place that was very special. Where that starting place came from is the question underneath all the others, and it remains as open now as it was when Boltzmann first formulated the statistical interpretation of entropy in the 1870s. There is one more layer at the bottom. The Planck time, approximately 5.39 times 10 to the negative 44th seconds, is the smallest interval at which current physical theories produce meaningful results. Below that scale, the equations break down. The concept of duration may not apply at all, not because instruments are too crude to resolve smaller intervals, but because the mathematics ceases to describe anything coherent at finer resolution. Carlo Rovelli has argued that time at the Planck scale is not a continuous flow, but a discrete sequence of quantum transitions. Between transitions, there is no time, not slow time, not frozen time, no time at all. Compare this to a film projected at 24 frames per second. Between the frames, the screen is dark. The story exists only in the frames themselves, and the smoothness of the experience is a product of human perceptual limits. Slow the projector below a certain threshold, and the gaps become visible. The continuity breaks. You see what the illusion was made of. Planck time is, in this picture, the frame rate of reality itself. The universe is reconstructed roughly 10 to the 43rd times per second. At the most fundamental level, there are only frames. Between them, there is nothing for time to do. What does the reconstructing is the question that lurks beneath all the others, and it has no current answer. If reality at its smallest scale is something like a discrete sequence of computational updates, then the question of what is being computed becomes inseparable from the question of what reality is made of. John Wheeler, who spent 6 decades at the heart of theoretical physics, arrived at a tentative answer in 1989. He called it from bit. Every physical quantity, every property of every particle, every value of every field is registered ultimately as a yes or no answer to a binary question. A particle is detected or not detected. A spin returns up or down. A photon arrives or does not. At the level of fundamental physical interaction, the universe communicates in binary. Wheeler's claim went further than this observation. He argued that information is ontologically prior to matter. The particle is not a thing that happens to carry information. The particle is what you get when the universe answers a binary question. Matter is crystallized information. Space is the geometry of informational relationships. The familiar furniture of physical reality, atoms and energy and forces, is the visible surface of a deeper structure made of distinctions. If reality is built from information, the question of its origin shifts shape. The relevant question is no longer what physical object existed first. It is what question was asked first. This connection between physics and information has tightened considerably in the last 2 decades. Gerard Hooft and Leonard Susskind, working independently in the early 1990s, proposed what is now called the holographic principle. The claim is that all the information required to describe the physics of any 3-dimensional region of space is completely encoded on the 2-dimensional boundary surrounding that region. The interior is not where the information lives. The boundary is. The principle emerged from an unlikely source, the thermodynamics of black holes. Stephen Hawking had shown in the 1970s that black holes have entropy, and that the entropy scales with the area of the event horizon, not the volume enclosed inside it. The information about everything that ever fell into the black hole is somehow stored on the surface, not in the depths. Hooft and Susskind argued that this is not a quirk of black holes. It is a general feature of how reality stores information. The entire 3-dimensional universe could in principle be encoded on a 2-dimensional boundary with 1 bit of information per Planck-sized area. Imagine a snow globe. The figures inside appear to occupy 3 dimensions. But if the holographic principle applies, the entire interior is a projection of information stored on the glass surface. The depth is real in a functional sense, in that it produces consistent observations and reliable physics, but it is not where the information actually resides. The reality is the surface. This is not a metaphor in the loose sense. It is a mathematical statement about how information is organized in spacetime, and it has been derived rigorously in specific cases such as the correspondence between certain string theories and certain quantum field theories on their boundaries. The 3-dimensional space we move through may itself be a projection of a 2-dimensional informational structure, not a simulation in the science fiction sense of a computer running a program, a mathematical fact about where the information is stored. But information is not free. Information has a physical cost, and that cost connects directly to why reality cannot simply persist without doing anything. In 1961, Rolf Landauer, working at IBM, proved a result that has come to be called Landauer's principle. The act of erasing 1 bit of information has an irreducible thermodynamic cost. No matter how efficient your technology becomes, you cannot reduce that cost to 0. Erasing information always releases heat, and the minimum amount is set by the temperature and a fundamental constant. When you erase a bit, you reset a two-state system to a known configuration. This is irreversible. The number of possible states decreases by 1. By the second law of thermodynamics, reducing the number of possible states inside a system requires a corresponding increase in the entropy of the surrounding environment. The minimum energy released per erased bit is the temperature multiplied by the natural logarithm of 2, multiplied by the Boltzmann constant. This number cannot be smaller, regardless of engineering ingenuity. The implication is that thinking has a thermodynamic price. Computation burns fuel. Every time a bit is erased and reset, heat is released. Not because of inefficiency, because of physics. A perfect, lossless computer still emits heat when it processes information. The universe has been processing information since the Big Bang, and every quantum interaction is in some sense a computation that pays the thermodynamic price of its own operation. Information is not merely a description of reality. It is what reality is made of, and reality has been spending itself to think since the first Planck interval. This connects to a discovery from 2013 that draws the link between information and the geometry of spacetime tighter than any previous result. Juan Modesena and Leonard Susskind proposed what is now called the ER equals EPR conjecture. The claim is that wormholes, the tunnels through spacetime first described by Einstein and Rosen in 1935, are mathematically identical to quantum entanglement, the correlation between distant particles first described by Einstein, Podolsky, and Rosen in the same year. The implication is that entanglement is geometry. The fabric of space is woven from quantum entanglement between subsystems. Remove the entanglement, and the space between regions does not become large. It ceases to exist. The spatial separation between 2 points is not a primitive feature of the universe. It is a derived property that emerges from the pattern of informational connections between them. Picture a fishing net. The knots are the systems. The strings are the entanglement. Cut the strings, and the knots stop forming a net. They become unrelated objects with no spatial relationship to each other. Space is that net. Entanglement is what holds it together. Space is not the container in which physics happens. Space is the consequence of informational relationships between quantum systems. And if those relationships were severed, the space itself would dissolve. This means reality is not stable because space is solid. Reality holds its shape because the informational connections remain intact. The structure is not a fixed fact. It is an ongoing process. Stop the process, sever the connections, and the structure unravels. The universe is not a static stage on which events occur. It is a continuously updating pattern of relationships, maintained moment by moment by the interactions that constitute it. But this raises a question that physics is currently unable to answer. If reality is information, and information requires interaction to be registered, and interaction requires systems to participate in the registering, then who or what reads the information at the most fundamental level? The double-slit experiment, performed countless times since the early 20th century, suggests that what counts as a measurement is not a matter of conscious observation in the human sense. It is a matter of whether the relevant information is, even in principle, available somewhere in the universe. A particle fired at a barrier with 2 slits, with no detector in place, produces an interference pattern on the screen behind. The particle passes through both slits simultaneously and interferes with itself. Place a detector at the slits, and the interference pattern vanishes. The particle behaves like a classical object, going through one slit or the other. Modern detectors can interact with the particle at the theoretical minimum of disturbance, and the interference still vanishes the moment which path information becomes available, no matter how indirectly. The presence of information about the path, not the physical disturbance of the particle, determines the outcome. Reality arranges itself differently, depending on whether information about it exists in retrievable form anywhere in the universe. This is not a statement about consciousness. It is a statement about the role that information itself plays in constituting physical events. The delayed choice version of the experiment, proposed by John Wheeler in 1978 and confirmed experimentally by Alain Aspect's team in France in 2007, shows something even stranger. The decision about whether to extract which path information can be made after the particle has already passed through the slits. By any ordinary understanding, the particle has already either gone through one slit or both by the time the experimenter chooses what kind of measurement to make. Yet the choice made later determines the behavior of the particle earlier. When the experimenter chooses to extract path information, no interference pattern appears. When the experimenter chooses not to, the interference pattern is present. The past behavior of the particle is not fixed until a measurement is made in the present. The history is not written until someone decides to read it. Wheeler described the universe as participatory in a very specific physical sense. Observations made now contribute to the constitution of what happened then. The past is not a fixed record waiting to be discovered. It is a structure that the present helps to bring into being. This participatory character of physical events has driven some physicists to a conclusion that is harder to dismiss than it first appears. The interpretation called Cubism, short for quantum Bayesianism, was developed in a foundational paper by Christopher Fuchs, Rudiger Schock, and David Mermin in 2001. The central claim is that the wave function is not a description of an objective external reality at all. It is a description of the beliefs and expectations that a particular agent holds about their future interactions with the world. Compare this to a weather forecast. A forecast is not the weather. It is a structured representation of what a specific forecaster expects the weather to do, given the information they currently possess. In Cubism, every quantum state assignment functions in this way. The collapse of the wave function is not a physical event happening to a particle. It is an update to the agent's expectations when new information arrives. This dissolves the measurement problem entirely, but at a cost most physicists have been reluctant to pay. Quantum mechanics, on this reading, is not a description of what happens in the universe. It is a tool that agents use to navigate their experiences. The objective territory may not exist independently of the maps that observers draw of it. You might object that physics must describe something objective, some shared reality that exists whether anyone is watching or not. That is a reasonable position. It is also the position that physicists have held for 100 years while the measurement problem has remained unsolved. The discomfort of the alternative is not, by itself, evidence against it. These results converge on a point that ties together the entire arc of this exploration. The classical, definite, structured reality of everyday experience is not a default condition of the universe. It is a state continuously constituted through interaction. Strip away every system capable of registering information about another system, and what remains is not nothing in the philosophical sense. What remains is a quantum substrate of pure possibility, a superposition of all configurations with no definite values, no located particles, no specific outcomes. This is the picture that emerges when the threads from quantum field theory, general relativity, information theory, and quantum measurement are pulled together honestly. The vacuum is metastable. The constants of nature sit at improbable values that no deeper theory has been able to derive. The cosmological constant disagrees with quantum field theory predictions by a factor so large it has no precedent. The fundamental equation governing the wave function of the universe contains no time. Space itself appears to be woven from quantum entanglement and may be discrete at the Planck scale. Information has thermodynamic weight. The past is not fully fixed until measurements in the present give it definition. And the act of asking why any of this exists turns out to be entangled with the existence of the asker. What physics has produced over the last century is not a complete description of reality. It is a series of results, each rigorously tested and independently verified, that together suggest the universe is far less solid, far less inevitable, and far less independent of observation than the classical worldview ever assumed. The ground beneath physical fact is not a foundation in any familiar sense. It is a process that keeps generating definite outcomes from indefinite possibilities, and the conditions under which this process continues are not fully understood by anyone. It is worth being explicit about what scientists currently do not know, because the open questions are where the most active research is happening, and the boundary of ignorance is where the next discoveries will come from. No one knows why the constants of nature have the values they have. The fine-tuning problem has multiple proposed answers, including the multiverse, the anthropic principle, and the mathematical universe hypothesis. But none of them are testable in the conventional sense. They reframe the question rather than resolving it. Whether some deeper theory will eventually derive these values from first principles, or whether the values are genuinely contingent and arbitrary, is unknown. No one knows whether our vacuum is truly metastable, or whether the calculations that suggest this are missing some piece of physics that will stabilize it. The mass of the Higgs boson sits in a range that produces metastability under current models. But those models may be incomplete. Supersymmetry, if it exists, could change the calculation. Other extensions of the standard model could too. Experiments at the Large Hadron Collider and at proposed future colliders are searching for evidence that would settle the question, and so far, they have found nothing that resolves it. No one knows how to reconcile general relativity with quantum mechanics, string theory, loop quantum gravity, and several other approaches each address parts of the problem, but none has produced a unique, testable prediction that distinguishes it from its competitors or from no theory at all. The interior of black holes and the moment of the Big Bang remain regions where both theories must apply and both break down. Active research continues, but the field has been working on this problem for over half a century without arriving at consensus. No one knows what the dark sector of the universe is made of. Approximately 27% of the universe consists of dark matter, and approximately 68% consists of dark energy. Together, they account for about 95% of the total energy content of the cosmos. We have detected their gravitational effects with high precision, but we have not directly identified what they are. Multiple experiments are underway to search for dark matter particles, and several space-based observatories are mapping the behavior of dark energy across cosmic time. The answers, if they come, will reshape cosmology significantly. No one knows whether the universe is finite or infinite, whether it had a true beginning or has always existed in some form, whether our cosmos is one among many or the only one, or whether the laws we observe are universal or local. Each of these questions is being approached through a combination of theoretical work and observational measurement, but each remains open, and no one knows what consciousness is, how it relates to physical processes, or what role, if any, observation plays in constituting reality at the most fundamental level. The hard problem of consciousness, as the philosopher David Chalmers named it in 1995, sits adjacent to the measurement problem in quantum mechanics, and the relationship between them remains unresolved. Some physicists treat the connection as illusory. Others suspect it is the central unsolved problem of science. What is striking is that none of these gaps are likely to close quietly. Each of them, when investigated carefully, leads outward into deeper questions rather than collapsing into clean answers. The pattern of physics over the last century has not been one of steadily filling in missing pieces of a known picture. It has been one of repeatedly discovering that the picture is larger and stranger than anyone had assumed, and that the assumptions on which earlier confidence rested were themselves unwarranted. This is not a discouraging picture. It is a generative one. The reason these questions remain interesting is precisely that they are not artifacts of confused thinking. They are real, well-posed problems that resist current methods. They drive the construction of new instruments, new theories, and new experimental designs. The next generation of gravitational wave detectors, space telescopes, particle accelerators, and quantum computing platforms will produce data that bears directly on several of these questions. Some answers will arrive in the coming decades. Others will probably take much longer. If there is a single thread that ties this entire exploration together, it is that the question of why reality exists has shifted in the last century from a question that physics refused to engage with to a question that physics is now circling at multiple levels simultaneously. The vacuum stability calculations, the fine-tuning observations, the cosmological constant problem, the holographic principle, the relational interpretation, the mathematical universe hypothesis, the participatory measurement results. These are not separate puzzles. They are different facets of the same underlying problem, viewed from different angles by researchers using different tools. What remains genuinely interesting is that the more carefully physics looks, the less the universe resembles a self-sufficient object that exists for its own reasons. It increasingly resembles a process whose continued operation depends on conditions that no one yet fully understands. Whether those conditions will eventually be explained, whether they were established by some deeper structure, or whether they are themselves brute facts that will simply have to be accepted, is one of the open questions of contemporary science. Sit with that for a moment, because it is a strange place to have arrived. Physics began as the study of motion, of falling apples and orbiting planets. It became the study of fields and forces, then of particles and probabilities, then of geometry and information. At each stage, the subject matter became less concrete and more relational. The progression has not stopped. The current frontier is a relationship between observers and the observed, between information and geometry, between possibility and actuality. Wherever this is heading, it does not appear to be heading back toward a comfortable classical worldview in which solid objects exist independently of their measurement. What it is heading toward is harder to say. The honest answer is that no one knows. The most precisely tested theory in scientific history does not know what it is describing. The most successful theory of gravity cannot be reconciled with the most successful theory of matter. The fundamental equation of cosmology contains no time. The boundary between observer and observed is not where classical intuition placed it, and the question of why any of this exists, rather than nothing existing in its place, remains, after 3 centuries of formal investigation, exactly where Leibniz left it. This is the state of the field. It is not what most people imagine when they imagine science. Science is often presented as a steadily advancing front of certainty, gradually conquering ignorance. The reality at the frontier is messier and stranger than that. The frontier is where the well-tested theories run out, where competing interpretations remain mathematically indistinguishable, and where genuinely fundamental questions sit unanswered for generations. If anything in this exploration leaves a lasting impression, let it be this: the universe you experience as solid, definite, and reliable is the visible surface of a process that physics is still struggling to understand. The atoms that make up your body, the light that enters your eyes, the time that you experience as flowing forward, the space in which you move, are all consequences of an underlying structure whose ultimate nature remains uncertain. That uncertainty is not a failure of science. It is the current state of the most rigorous investigation any species has ever conducted into the nature of its own existence. The investigation continues. New experiments are being designed. New theories are being developed. New observations are being collected. The questions raised in this discussion will be refined, expanded, and partially answered over the coming decades, and the answers will almost certainly raise further questions that no one has yet thought to ask. That is the nature of science at the frontier, and it is the reason this remains, after everything, one of the most genuinely interesting problems anyone has ever worked on. If this exploration has changed how you think about the ground beneath your feet, even slightly, consider sharing it with someone else who finds these questions worth sitting with. Subscribe if you want to follow further investigations into the strange territory at the edge of physics. The questions do not get easier the further in you go, but they do get more interesting, and the conversation about them is worth having out loud. The universe did not have to exist. The fact that it does, and the fact that we are here to notice that it does, is the most remarkable observation any of us will ever make. Whatever the final answer turns out to be, if there is one, the questions themselves are worth the time it takes to understand them.